Good afternoon, everybody. We're just going to give it a few seconds here, maybe a minute or so while people are still joining on, and we'll get started. So just sit tight for a second. Okay. So welcome, everybody. Good afternoon and early happy Thanksgiving. So I probably know most of you. I can't see your pictures, but I probably know most of you already. But in case I don't, so I'm Matt Francis. I'm a chemistry professor at UC Berkeley, and I'm also the chair of the chemistry department. And my background is in organic chemistry. And what my research lab does is we do protein science. We develop ways to modify proteins, and we use proteins to make new types of drugs, new types of materials, and a lot of applications in understanding how light harvesting works. And so this is sort of the chemical biology of this. And what I teach is organic chemistry and chemical biology, both at the undergraduate and graduate levels. And this intersects really well with one of my favorite hobbies, which is cooking. When I was a graduate student, I started really getting into cooking. I used to go over to a postdoc's house back in grad school, and we would, make bread on Sundays, and we had these really geeky experimentals. We would write about it and test all the variables and things like that. And it's something I just never stopped doing. It's something that I've always loved to do. It's a little bit like doing chemistry and doing experiments, except the results are often more successful and rarely lethal. So, this sort of lends itself to really blending the two together. And I started probably about 15 years ago giving talks on the chemistry of cooking. I do this both at UC Berkeley. Sometimes we teach a type of class called a decal, which is an undergraduate-led course. We've done that in the past, and I also sometimes give talks in the community about this. And the reason for it is that it's a really interesting way to teach people a lot of chemical principles, a lot of ideas in chemistry. And the lab is actually something people have already done. A lot of people have already done the experiments, if you will, that go along with the material. And so it's a really nice way to connect with people. And so it's something that I've enjoyed, and I hope you enjoy the presentation this afternoon. I always start these by saying, does understanding chemistry or being a chemist make you a better cook? And my answer usually is no, not really, or at least not necessarily. What we're not going to do is distill everything down into, a set of, really sterile chemical reactions and things like that. I think the beauty of cooking is that there's so many molecules involved, there's so much complexity involved that it's different every single time. And I think that's why it's such an interesting thing to do. I think that's what makes food so interesting to us. And so really, it isn't that we're going to use chemistry to try to fix all the problems, so to speak. Rather, the way I put it is understanding chemistry is a little bit like taking an art history course before you go to a museum. That if you understand the context of the art, the history of the people who made the art, a lot of the things that were going on at the time, you get so much more out of it. And that's really why I'm into using chemistry in the kitchen. It just makes everything more fun and interesting when you actually see these processes happening. So let's dive right in. So as I said, I'm a chemical biologist. And so these are just looking at the molecules that we study in chemical biology, which are the molecules that we also happen to eat. Just going through these very quickly, carbohydrates are molecules that are made of these carbon skeletons. If you're not familiar with chemical structures, carbons are located at all the vertices that you see in these molecules. And you'll see that these are decorated with all of these OH groups that interact very readily and bond with water molecules. And so a hallmark of carbohydrates is they tend to be very water soluble, at least for the most part. And this makes them fast transportable energy. They're readily transported through the blood, and they are used for energy very quickly. And in the terms of cooking, this is known as sugar or starch, and then the insoluble variant, which is fiber. We also have fats. Fats are long chains of carbons like this. This would be a so-called saturated fat because there are no double bonds. And fats are actually meant more for long-term storage. So the fact that they have all these CH bonds all through these lengths like this makes them not interact well with water molecules. they're generally insoluble in water, and so you need some type of mechanism to transport these around. So these are more intended for permanent energy storage. This is energy storage for a rainy day, which may or may not ever come. And fats are actually what gives food a lot of its sort of texture. They are flavor carriers. They're a very important part of what makes food rewarding to eat. And so these are in the forms of oils, butter, egg yolks, and they're found in meats and whole grains as well. Today, we're going to talk a lot more about this one, though, which is proteins. Proteins, in my opinion, are the most interesting molecules in nature. They can do almost anything. They can accelerate chemical reactions. They can form structures. They can be motors that move. They have all kinds of functions that are fascinating in biology. They're also one of the major three components of what we eat. And proteins are made of amino acids. We'll get more into this in a minute. And they're in these polymer chains, which are called polypeptides. And each of these units, so the blue one, and then the black one, and then the blue one again, these are all the individual amino acids along this chain. And as we'll see in a moment, the different amino acid side chains stick out here, these groups that append from that chain, and those give these different types of properties that become very important in what they do biologically in terms of function, but also sometimes in terms of their cooking properties. Where we run into proteins, of course, is in meats, eggs, tofu, dairy, grains, and beans. And of course, you need proteins. You can use these directly for energy, but you primarily need the proteins. You're going to break these down and use the building blocks to make your own proteins. And then there's a lot of small molecules. We're not going to talk much about these today, but of course, many small molecules like vitamins, minerals, there is cholesterol, water that are also very important. So understanding these molecules is key to cooking. It's also, fundamental to understanding biology. And so diving right into the proteins, as I said before, are made of these amino acids. You can see them in this chain. So going from this nitrogen atom over to this carbon double bond O or carbonyl group here, this would be one single amino acid. And these amino acids are linked in this chain like this. And every protein has a certain set of these side chains that sticks out that give it its own personality, okay? This usually doesn't come across as something we perceive as taste, but this actually has a lot to do with how they function, as I said, in biology. Now, these amino acids come in two different types. There's the so-called essential amino acids. The essential amino acids are these in the top. These are amino acids you cannot make. They're actually ones you have to get from your diet. These are the branched amino acids, the ones that have these benzene rings, aromatic rings in them, and the sulfur-containing ones. And then there are also non-essential amino acids. These are amino acids that you have biochemistry in your body to produce. And so these are the more simple amino acids, and it's actually a pretty pathetic amount if you actually think about it. So some organisms, such as plants and bacteria, can manufacture all of these amino acids. Most mammals like us cannot do that. Really, two that historically are very important are methionine and lysine. These are the limiting amino acids in many foods. You might have heard of this before, that if you eat a diet that is very high in legumes, so things like beans and so forth, you can actually develop deficiencies in methionine, one of the essential amino acids right over here. Or if you eat a diet that is solely consisting of grains, let's say rice or something like that, you can actually be limiting in lysine, which is another of the essential amino acids over here. And it's kind of interesting. This has led to a lot of combinations throughout the ages. People have naturally found that if you mix legumes and grains, such as lentils and rice, for example, or beans and corn in Mesoamerica, or in the USA, peanut butter and bread, if you put these together, you actually get both of these limiting legumes and a full set of the amino acids. So this is where you see these a lot of times in nutrition. Well, what we're often concerned about is the flavor that they have. A lot of these amino acids, and particularly one, glutamate, glutamic acid, which is right down here, this black one, is something that your tongue perceives directly as your fifth taste. So in addition to sweet, salty, bitter, and sour, you have a direct taste receptor for umami, this savory flavor, which is a direct response to glutamic acid. And that tells you that proteins were present in the food, and they've been broken down in various ways into those amino acids. So these are neurotransmitters often. Glutamate is a neurotransmitter. It's used by the body in the process of memory and learning. It can be turned into gamma aminobutyric acid here. This is also, again, as I said, something that you can taste directly, and this is something you can even add directly to food in the case of accent, which is just MSG. MSG, if you've ever tasted it straight, tastes just like chicken, as one might guess. It's actually pretty delicious, again, as one might guess. But there are others. And so one of these is tyrosine on the right. That's my favorite amino acid of all. Tyrosine is the precursor that's turned biochemically into dopamine, which is a reward molecule. It's also used for neuromotor control. And the one that you usually hear about associated with Thanksgiving is tryptophan, this amino acid here that has this interesting double ring chain with this nitrogen in it here. It's called an indole ring. And tryptophan is indeed the biochemical precursor to the neurotransmitter serotonin. And serotonin is a molecule that is associated with well-being and happiness. And in fact, many drug molecules are serotonin uptake inhibitors that prevent its destruction in the brain that are used therapeutically to treat depression and a number of other conditions. And so what a lot of people will say is that, when you have a Thanksgiving dinner, you eat all that turkey and you have all this tryptophan, and that makes you sleepy. And that's a reasonable thing to say because you have this abundance of tryptophan, so maybe your body makes more serotonin than usual. That is actually the first myth that we'll debunk today, that most people say that that is not why you get the Thanksgiving food coma, rather, there are many other foods that have way more tryptophan than turkey that are not associated with drowsiness. For example, eggs have a lot of tryptophan in them. Shrimp has a lot of tryptophan in it, much more than turkey, as it turns out. And so a lot of these other foods are not associated with that. The real reason why people usually have the food coma on Thanksgiving is because the average American eats 3,000 calories in one single sitting. And so when you eat all those calories, then your body has to go into recovery mode and spend a lot of energy digesting all of that food. And so that is probably the more realistic reason why you have the food coma after the meal. Okay, so proteins themselves have these folded structures, and this is going to be important to what we're going to talk about today, and it's a really important thing to think about and keep in mind when you think about cooking. And so we can draw these different ways. On the left side, I've drawn this as a chemist might do, where I've drawn all the atoms, at least all the non-hydrogen atoms. And so nitrogens are blue, oxygens are red, the carbons in this are these gray ones. And so you can kind of see how these look, and as a chemist, we can move these around and study their properties. A lot of times it's very convenient to ignore the parts sticking out and just focus on, if I just go back a slide or two, the backbone itself. And we're going to erase the side chains. And so that's actually this one here. And so you can kind of see that you can think about this as a little string. It's color coded with rainbow colors and sort of the order that these amino acids are linked in the chain like this. And you can start to see that this has a specific kind of fold to it, that these sort of turn around in this sort of snake-like pattern. And what we often do is we represent this with things like these helices, alpha helices or beta sheets. These are the basic elements of protein structure. And if you study proteins for a while, you can kind of look at this and figure out which one this might be, that this particular way, exactly how these are all folded up, is a type of fold that you find in the protein myoglobin. And it folds up in such a way that it holds this yellow group here, which is a heme group. This is a group that contains iron. There's an iron atom in the center of this. And that iron atom is used to transport or store oxygen. Okay, I should say store. Hemoglobin in the blood is a protein that transfers oxygen around. Myoglobin, sorry if I said hemoglobin a second ago, myoglobin is a relative of that. It's a single protein that just stores oxygen. And this protein is actually found in muscle tissue quite abundantly. And this leads us to another thing that's associated with Thanksgiving and poultry in general, which is this concept that you have the light meat and the dark meat, or white meat and dark meat. And so when you look at the different kinds, so turkey legs, turkey thighs, if you're having turkey for Thanksgiving, is what we would call dark meat. You can see it's actually darker here in the raw form and is also darker after it's been cooked. And then turkey breasts here. This is also a pet peeve of mine. Turkeys, all birds, in fact, are not mammals. Only mammals have breast tissue. So this actually should not be called turkey breast. It's actually a pectoralis muscle, a pec muscle. So next time you go to the butcher, ask them for a pack of turkey pecs or chicken pecs and see what they do, because that's the more appropriate term. But this muscle is actually what we would call white meat or light meat, because it actually does not have the same color. The difference between the two is actually the myoglobin level. It's the amount or the number of these proteins that are present per amount of tissue. And it's in fact the iron atom that's found in myoglobin that's actually giving this darker color here. And so the reason that this difference exists is that, again, I told you myoglobin is a storage protein. It stores oxygen that muscles that surround it need to use, especially in terms when they're used for endurance, times when they're used for endurance. So turkeys, as it turns out here in Berkeley, we have turkeys everywhere. I saw at least a dozen turkeys this morning in my yard. They're all over the place. So you can actually observe them and their behavior. And one thing that you notice is turkeys really don't fly very much. They can, but they rarely do so. And when they do that, they're usually just trying to get out of trouble, and it's not a long time thing. They don't fly for long distances. And so turkeys don't really need a lot of myoglobin that's in these pectoralis muscles, which drive the wings. That's the same for chickens. Chickens also rarely fly. They can flutter around to get out of trouble, but they usually don't fly for long distances. So they have not evolved to have a lot of myoglobin here, and that's why this is lighter in color. In contrast, they spend all day roaming around on the legs and thighs. They're looking around for food. And so that's why these long endurance muscles here actually have more myoglobin in them. This also explains why other animals, such as the mighty duck, shown here on the right, don't have white meat at all. There's no such thing as white meat on a duck. And the reason for that is because ducks, birds like ducks, migrate for thousands of miles. And so they have very myoglobin-rich tissue like this, where they actually have a high abundance of iron, so they can store oxygen and use that for those long distances so that they have to travel. So that's sort of why you have these differences in the different types of meat when you cook them. I also forgot to mention this at the beginning. If you'd like to ask questions during the presentation, please do so. Instead of using the chat function, which is a little bit hard for me to monitor, there's a Q&A function that you should see on Zoom. So please feel free to use that and type your questions in, and I can address any questions that you have. Okay. Okay, so the other important thing about proteins that I stressed is the way they're folded, that myoglobin only works, and in fact, it only holds heme properly when it's folded in exactly this right way. That fold of this protein is what gives it its actual biological function. And generally speaking, in cooking, we disrupt this folded structure, that we do a number of things in the kitchen. We heat food, or sometimes we use friction. That would be like kneading bread dough. We use acid and base. This would be like making ceviche or something where you add citrus to food to cook it, or enzymes like in cheese making. A variety of these kinds of things causes the structure to be disrupted, and you get an unfolded protein that no longer has its original biological function. So as we cook our food, we lose that native function. And one of the important things that's happening is that then you have these aggregate. Once they have unfolded, they tend to lose their solubility in water. They become much, much less soluble. They tend to come together in these long fibers, and they form these long insoluble fibers like this. And as these fibers start to form in your food, this starts to scatter light. And so one of the things that you notice when you cook food in general, think about a piece of fish or a piece of steak, is that raw meat has that sort of translucency to it. You can kind of see through it a little bit. You can see light penetrate that a little bit. But when you cook it, generally that's lost. And that is lost because once these proteins form these insoluble fibers, light scatters back out again, and that actually is what you see coming back at you. And so you sort of lose that property. Just to catch up with a couple of the things on the questions. So one of the things is, what causes dark meat to be more moist? That's a great question. I'm going to come to that a little bit later on. It's because there's another protein, a really important protein that's more abundant in dark meat in general that I'll discuss later on. So I will try to answer your question later on. So a couple of people are asking me that, why is it tasting better? And also great point in the question, the Q&A as well, about Beyond Burger, or more specifically, I think the Impossible Burger. Yes, what they're trying to do is use culturing methods to make heme-containing protein that actually can mimic the flavor that you get when you have those heme molecules actually are oxidized, I think is what the way the theory goes, and so they have a specific flavor to them. So that's what they're trying to recapture. So absolutely. So you have this scattering, which makes the food turn opaque. And so you can actually see that. This is a great example here. It's my favorite example, and one that everybody knows, which is cooking eggs. And so when you cook eggs, if you either fry them in a pan, or here what I'm showing is you take eggs, grade A eggs from the refrigerator, and put them in boiling water. And if you did that and cut this open, this is not an experiment I did myself, but this is one that I found online. You actually can see how over different periods of time, the eggs are cooking on the inside. And the first thing that we're talking about here is, of course, you know that the egg white, when it's uncooked, is translucent. You can see right through it, but you can see that as it starts to denature, as those protein fibers form, it becomes opaque. And so that's the white that you see here, the white of the egg on the outside. And the other thing that you can see is that the cooking process, maybe not surprisingly, starts on the outside and transfers into the inside. And so heat has to make its way from the outer part of the shell all the way through to the center in order to cook the center. And so the outside of the food cooks first. That's generally true for a lot of things. And that's what we'll get into just in a moment for Thanksgiving cooking. So each of you probably has your own place where you like to stop your eggs. I actually like 7 minutes and 35 seconds. And so that's when I get the nice fully set white on the outside like this, and actually the nice creamy yolk on the inside like this. And so that's to my taste. Everybody has a certain different place that they like to come on here, but this shows that overall process. So there are a number of things, though, that cause these to happen with greater or slower rates, and this causes some variability in your cooking. I once had a really interesting discussion. I was on a panel discussion with somebody who actually knows what they're doing from Chez Panisse, as it turns out. We got in this spirited debate about eggs because they were saying the perfect egg is soft-boiled egg like this, or boiled in the shell egg like this, is after 4 minutes. And I'm like, no way, that's way too runny. I like it, 7:35. That's when it's set to my taste. And what we finally figured out is that we both liked our eggs the same way. It's just that my eggs, like probably most of you, come from the refrigerator or the supermarket, so they're cold. But their eggs don't. They actually probably got them fresh from the chicken earlier that day. And so their eggs are room temperature. And so they actually have a completely different set of timing. And so my point with this is, your cooking rates that you're going to depend, and how this is going to look, is going to depend on a lot of variables that are very hard to predict. So you can't come up with some type of mathematical formula to tell you how to cook a food in the kitchen just based on any certain property. So for example, the surface area or the volume have a lot to do with how fast they cook. The density of the food has to do a lot with how fast the heat transfers to the center of that food. As I point out, my Chez Panisse egg example, the cooking temperature versus the food temperature. What is the differential in temperature that controls how fast the heat moves through it? And then another one that we'll get to a little bit later is the heat transfer medium, meaning these eggs are cooked in boiling water. Water transfers heat very rapidly versus if you use air, like you do in the oven, that's a much slower transfer of heat. And so that actually has a lot to do with it as well. So there's many, many variables here. These are the things that over the years you start to master when you're cooking. So just as an example of this, if we think about, cooking here, and we like something around the 7.5 minute range, but now consider for a moment, what if we were to cook an ostrich egg? An ostrich egg on the right side here is the same volume and mass really of 24 chicken eggs. And so maybe the quick thing you think in your mind is, well, let's multiply the cooking time by 24. So if it's 7.5 minutes, it would be whatever 7 times 24 is. Never do math in front of an audience. And so that might be a reasonable idea. But as I said earlier, that's not the way it works, because this has a different surface to volume ratio than this does. And so really, it turns out that you boil an ostrich egg for 50 minutes. If you want it soft boiled, or hard boiled is 1.5 to 2 hours. So definitely a lot longer. It takes way more time for the heat to get to the center. So that's one of my points. And the second point is that it's not that predictable. You can't just use a simple multiplier here to figure out how long you have to cook this. You kind of have to do it a little bit by trial and error. Okay, so looking at this now for Thanksgiving, that is a similar problem, because most of you who cook probably fairly regularly cook things like small casseroles. You cook pies, you might bake bread, or you might make a chicken in the oven. And so you're most familiar with how to cook those foods. You know kind of how to set your oven to get the right results for those kind of foods. And then one day a year, you have to suddenly do this, where you have this gigantic beast of a bird. This one has been photoshopped to emphasize its size, but this might be a pterodactyl size bird. But all of a sudden, you have to cook this really, really large object, which might even be stuffed with something. And so this is very different from your normal cooking experience that you have from day to day, at least for most people. So if we write this out like a chemist, so this is my chemistry equation of my starting material on the left, which is the raw turkey, and my desired product on the right. So this nice brown turkey over here. And so really, as the cooking process occurs, what's important for this cooking this turkey are the sort of things we've talked about. So first of all, we didn't talk about this. The bacteria are killed. All poultry often has salmonella bacteria associated with it. And so the bacteria are killed by the heat of the oven. So that's very important. Generally speaking, you want to go well above 140 degrees. Most people for things like turkeys say go a little bit higher, like 160 degrees, to make sure that all the bacteria are killed. It actually depends on how long it's held at that temperature is what it really comes down to. But you do need to make sure you do that. And one thing I'll caution you about is if you do stuff the bird, if you put stuffing on the inside, be very careful because the inside cooks last. It takes a long time to cook that stuffing up, and that stuffing's been sitting there in contact with the bacteria for a long period of time. And so you want to make sure you cook the stuffing all the way through so you don't actually have a bacteria associated with it. So that's really important. The second is that you're going to improve the texture by solidifying those fibers, by having those insoluble protein fibers form. And then one of the things that's going to happen on the outside to give you this delicious crispy skin, one of those things is you're going to start to break down these proteins into their individual amino acid components. Among those individual amino acid components are, once again, glutamate. So you're actually going to produce some degree of MSG naturally by breaking down the proteins on the surface of the bird. It turns out there are many, many foods and many processes associated with foods in cheese making, soy sauce, all kinds of things where they are specifically designed to release glutamate from the food and make them taste savory. And then the other thing that's causing the browning here, I'm going to show an example of this a little bit later, are these so-called Maillard reactions. These are reactions that occur between the protein, nitrogen, and the carbohydrates. They cause these brown colors and hundreds of different flavor and aroma molecules that give this the smell and the taste that you associated with roasting. So that's all the good side. And so you want this crispy, delicious skin on the outside. You want your stuffing to be cooked. You want to have this to be nice and juicy. Be careful not to undercook down here on the thighs and so forth. That's where you usually check the temperature. But the other thing that you don't want to do is keep going, because if you overcook, then what happens is that the muscles have these fibers in them, and the fibers will start to contract at a certain temperature, generally between 140 degrees to 150 degrees. And as they contract, they squeeze out the water. They squeeze out the water in the tissue, much like a sponge would do. And so you'll start to see the water come out of this. You've probably seen this happen if you cook chicken or steak or mushrooms in a skillet. They're cooking just fine, and then you hit a certain point where all this liquid comes out, and all of a sudden it's kind of like a soup in there for a little bit, and then you boil that off, and then you can continue. That is that release point. That's where they actually hit that point where there's a contraction of the proteins or the muscle fibers or both, and that releases the water. Okay, so that's what you don't want to do. And that is often what inadvertently happens here in the chicken pec or the turkey pec muscles, or we'll say breast for today. The turkey breast is often dry and overcooked because it's actually gone past these temperatures. Okay. One of the questions in the chat is there one protein associated with freshness? I would say not necessarily. And what changes chemically when food goes stale? Couple things. One of them that happens is fats can go rancid. That's one of the most serious in terms of taste. So fats have many fats have double bonds in them, and they react with oxygen in the air. And over time, that causes the fats to cleave. They form molecules called aldehydes and acids, and aldehydes and acids don't smell that good, especially carboxylic acids tend to smell fairly nasty. And so when you say something is rancid or not fresh, it's often because the fat molecules are actually what have done that. Of course, you can have bacteria grow in the food, which can cause spoilage. That's another thing that can do that. And a few other things. In general, one other thing about staleness is that some of the fresh molecules, the ones that are present in the food, will start to degrade or evaporate over time. So things like spices also go stale, and that's because they lose those volatile molecules and they no longer have the same punch that they used to. So many things cause staleness, but really the main thing people worry about is that the rancidity of the fats. Okay. Okay, so we talked about the contraction of these proteins, and so this is two more examples that you're probably familiar with. So meat down here, this does have the muscle fibers, of course, and as we take a steak and cook it past that point, you can see this is actually the same piece cut in half, but you can see that it's much less thick, and so it's released the water. Same up here for these eggs, these delicious, soft, pillowy eggs, which are perfectly cooked. But if you continue to cook these in the pan, as I always did when I was younger, you will lose all that water and you form these dried, shriveled up, like hotel eggs, which aren't so good. And so again, both of these are what you get when you overheat the food and you lose the water. So the trick is with the turkey, given all these variables, that compared to a chicken, it's got much greater volume, of course. but it also has a higher surface area. So heat can hit more surface area of it to cook it, but it has to transfer farther on the inside. And so this leads to a lot of different, variables and so forth. And so generally it leads to this principle here, which will serve you pretty well in the kitchen. And this works very well for poultry. This also works very well for things like bread and cakes and other things that you cook. And that is this general rule that the smaller the volume of the object, the higher the oven temperature should be. Okay, because the heat has to transfer less far in here. It doesn't take as long. And so I can get away with a higher temperature. A higher temperature is going to give me a better brown crust on the outside and have still enough time to get on the inside before this chicken burns. Okay, so chickens, I usually cook them 425 to 450. Judy Rogers used to do the Zuni Cafe, ran the Zuni Cafe in San Francisco. I use her recipe, and it's usually in that temperature range. And you cook these pretty fast for about an hour. But when you have something really big like a turkey, the goal is more the low and slow. Okay, where we're going to do this at a lower temperature, 350 all the way down to 325 sometimes, and we're going to cook this for a long period of time, up to 4 hours. Okay, so you're probably familiar with this if you've ever cooked a turkey before. They take a long time. The other thing you tend to do with a turkey that makes this worse is basting. So what you constantly do for a turkey is you open the oven more and more often as it cooks, and you suck up the liquid in the top and you squirt it on the top to baste it with the liquid that's in there. This actually really adds to your turkey cooking time, because every time you open that oven, you're losing a ton of heat. Okay, and so you actually have to then close it and wait for a while before the temperature to come back up to continue the cooking. So you can actually do yourself a disservice by basting your turkey too often. One tip I would have for you, I've done this myself and it works pretty well, is if you want to have a turkey and you want to cook the bottom side here, the sort of legs and thighs, and not overcook the turkey breasts on the top, what you can do is start the process with the turkey upside down. This works really well. Just put it upside down in your roasting rack. And that causes the juice to run down over the breast meat, which tends to be drier. Again, more on this in a little bit. And then you cook it for maybe, say, the first half. You can find online recipes for this. And then this can be a little bit of a kitchen operation, I'll tell you. But you get all the spatulas and tongs that you have, and then you turn the turkey over and finish cooking it and get this nice brown on the top. So that actually works really well to get moist turkey throughout. It also accelerates the cooking on this bottom side, which is sometimes slower to cook. So that's one trick. Now, one of the things I mentioned earlier is a lot of people stuff the turkey. Certainly we do where I grew up. And so putting stuffing in the turkey is really one of the worst things you can do in terms of the cooking speed, because now you made it even harder, because now it's a solid object. And so the heat has to transfer all the way to the center of that stuffing. So it can add up to an hour to your cooking time. What is a better idea is to cook it separately. So you can cook it in a separate pan, which works pretty well. I know it doesn't give the same flavor if you're in the bird stuffing person, but you can do that. Or one of the things you can do to your turkey is also stuff it with aluminum foil. I've tried this once. I'm not sure it's worth it, but you can try this. If you put aluminum foil in the turkey, that's actually a really good heat conductor, and so the heat from the oven conducts all the way in the center and cooks from the cavity side as well as the outside, is the theory behind that. And so you could try that as well. If you have a really big one, maybe that'll help cook it a little faster. Like I said, I've done that before. I don't really find it that big of a deal, but to each their own. Okay, so you can, the general thing I want to point out here is this lower temperature. So the larger this object and the more solid it is, the lower the temperature goes. If you want to take this to the extreme, that is probably this invention here called the turducken. The turducken is, there's some debate over where this originated. Some say the chef Paul Prudhomme came up with it. Some say Madden came up with it. I don't know. But what this is a sort of trio of animals here, where what you do is you have the turkey on the outside and you stuff it. Well, let's go and these aren't in the right order. You have a chicken in here that you debone, you put that inside a duck that you also take the bones out, and then you put the duck inside the turkey like this. I'm sorry if there are vegetarians in the audience. So we'll get to some more vegetarian friendly things in a little while. But you can make these, and they often put stuffing in here sort of as a plastering agent to make this solid object. I've actually never had one. But this is now very solid and very thick. And so you can see the cooking method here is 225 degrees. So the lowest temperature of all, again, going with the fact that it's the largest, most solid object. So lower your temperature so the heat has time to transfer the inside, and you cook this for, in this case, about 3 hours. Okay. Now, the other thing that you'll notice in this recipe, and in a lot of recipes, especially if you cook things like prime rib and many other things, and chickens too, is often they have this high heat blast step. And in this particular case, what we're going to do is we're going to hit this at high heat for 15 minutes, 500 degrees, very hot. And then we're going to turn the oven down and continue to cooking this. This is also how people often cook chickens, where they'll cook it closer to 500 and then reduce it down for the rest of the cooking time. Prime rib, you can do that as well. I personally am a big fan of what you call the reversed sear method. If I were doing this, I would probably start at the low temperature, cook this for a really long time, take it out of the oven, crank the oven up to a really high temperature and put it back and finish it with a very quick blast of heat at the end. I prefer that way. That's called a reverse sear. And that's how I make things like prime rib and so forth. And so why are we doing this? What is this high temperature step really for? And I think intuitively, a lot of you know that it's for this browning on the outside, that's what gives you this browned crust on here that has all those delicious properties we talked about earlier. But why is it so essential? And especially in a case like this, where we're cooking this at 225 degrees Celsius. And so just for a moment, I want to look at the organic chemistry of this. And I realize that the audience, some have more experience with organic chemistry than others. And so I'm not going to go through all the details of this. When we do our decal, sometimes we do. But we have these Maillard reactions that are reactions that occur between the carbohydrates and the amino acids of proteins. And these are reactions that involve sugars. Sugars, I showed structures like this earlier with all these OH groups, remember? And they actually can open up sometimes and form these, what we call aldehyde groups like this, and ketones as well, these carbon double bond oxygens like this. And we have a lot of nitrogens in our proteins. Let's say this nitrogen amino group of a lysine here. And these two groups can come together, that if I just focus on the red, this red oxygen and these two hydrogens, these can come together to make a water molecule that is released as these react with each other. And that forms a bond between this nitrogen and this sugar molecule. This bond right here, this nitrogen carbon double bond is formed, and we call this an imine in organic chemistry. And so these link the sugars to the proteins in a way that they weren't linked before. And once that happens, all kinds of really neat reactions can occur. For the aficionados, this amidori rearrangement is one of the important next steps, which shifts the double bond from here to here, then tautomerizes to form the ketone. So sorry to go to organic speak for a moment. And then this can actually fragment through a retroaldol reaction here, or all kinds of things like that. And these start to cyclize, they start to fragment, they lose more water molecules, and ultimately form many of these kinds of small molecules like this that have different smells, like butter, caramel, butterscotch, cracker, whatever that is. All these different molecules, again, are different every time you cook. And these are the things that give you the flavor of that brown crust. Okay, these are the Maillard browning reactions. Well, the thing I want to point out here is there's a couple of reasons why we need that high heat blast. The first is that these reactions themselves only occur between about 230 and 320 degrees Fahrenheit. So if I just go back, if I'm cooking my turducken at 325 or other types of things at those low temperatures, they really don't get high enough to hit this range. So they're not going to brown just simply because there's not enough heat to make these reactions go. So that's one reason. There's another reason, and it's actually probably more important, and that is that water is the enemy of browning. You cannot brown food if water is present, and that's for two reasons. The first reason is if water is around, especially bulk water, it's going to evaporate and take the heat with it, and it will continue to do that until it's gone. And so if you have something that is sitting in a pool of water, no matter how hot you heat your skillet, that water is going to evaporate and take the heat with it before the food on top of it can get any hotter than 212 degrees Fahrenheit or 100 degrees Celsius. Okay, so the water steals your heat. And so that's happening on the surface of a turkey or a chicken or something like that. The water will also steal the heat until it's all evaporated and gone. And then these reactions can reach the temperature where they can commence. The second reason water is the enemy is it is lost in this step. This is actually a reversible chemical step here. So are other steps along this process. And so if water is present, that tends to push this equilibrium to the left more. By Le Chatelier's principle, this will go to the right more if the water is removed. And so that is why water is the enemy of browning. So you have to get rid of it. So there's a couple ways to do this. We talked about using that high heat blast. So that basically dehydrates your food. Once that happens, then you're ready to go. A second way that you often see with poultry is and other foods is you put it in your refrigerator overnight and just let it sit there. And what you're doing is the refrigerator is actually dehydrating the skin for you. And so a lot of the water that was on there in the packaging is evaporated. And so you actually put it in the oven with a much drier turkey. So I recommend doing that rather than just unwrap it and put it straight in the oven. It usually gives you a browner crust on the outside. And there's a third way, which is to use a higher temperature in a different medium. And I'll show that in just a second. Okay, so these Maillard reactions are really key for putting these on there. And let's see, just catching up a little bit here with the oh, did I make I apologize. Yeah, thank you for pointing that out. I made a mistake. I think I said somewhere on my Maillard, somewhere on here, I made a mistake and got my Celsius and my Fahrenheit confused. I apologize for that, Americans. Okay, so does adding lemon to water change the boiling point or improve the Maillard reactions in any way? So you can add things to speed these up. Acid is one in the form of lemon juice, and the other is a tiny, tiny pinch of baking soda that you can use, a little base. These are often acid or base catalyzed reactions. Be very cautious with that because they can go out of control and you'll get a goopy mess. So for example, when you caramelize onions, which involves these same reactions, then you often can add those and that will make them go a little faster, but actually it doesn't really lead to a better result in the end because it gets all mushy. So be careful with that. Doesn't change the boiling point. If there's one thing you want to add that can help with caramelizing onions and things like that, in my opinion, it's salt, but it's not what you think. So there's also in one of the questions there about does adding salt increase the boiling temperature of water, right? And so we do this lab often in freshman chemistry. So yes, it does. It does. If you add salt to water, it'll actually raise its boiling point. But the amount of salt that you would normally add raises it by at maximum of degree and possibly less. You can actually calculate that. And so, so it really doesn't have that effect of making the water temperature hotter. What it does do though, adding some salt, it draws the water out. By osmosis, it actually accelerates the loss of water from the cells of the food. So when I caramelize onions, I add a pinch of salt and that makes the water come out. You can see this or do this with mushrooms, try it on your own. And you'll see a lot of water come out right after you do that and it evaporates it and gets it over with. And then you can get on with your browning process. So that's what I prefer to do for that. So yeah, thanks for asking the questions. Okay, so second generation turkey ideas. There are other ways to get around having this turkey cooking problem that are more efficient if you're willing to go a little away from tradition. One that I have done many times, this is usually how I fix chickens, but this also works great for turkeys, is called spatchcocking. Sounds like an unsavory word, but it's not. This is a process where you actually remove the spine of the bird with a pair of scissors and flatten it, open it up like a book like this, you can see here. And now you've actually gone from this sort of semi-spherical object into this sort of regular flat one, and this is much easier to cook. So this is a great way to cook it. Everything cooks very evenly like this, and you don't get the dry top and the bottom is not done yet. So I definitely recommend you try this. The only problem with this is a lot of people just really love the look of that turkey when you bring it to the table. And so I did this once for my family back in Ohio, and they were horrified by what I had done to the turkey, although they did eat all of it. So there is that. So you can try this. Another thing that's very popular is deep frying. Deep frying gets to the medium problem, where air in your oven is not very efficient at transferring heat by convection, versus oil is very efficient at transferring heat. And it can go to temperatures higher than water. Water can only go to 212 degrees Fahrenheit, but oil can go much higher. So I didn't look up what temperature to deep fry a turkey, but you can often go well above 300 degrees and get away with that. And so this is a great way to do it. Also, by its very nature, it keeps everything sort of juicy and sealed in there. It keeps the fat content high and all that kind of stuff. So this is a very popular method for turkey cooking. So I have had deep fried turkey. I've never done it, but it is delicious. I do want to caution you. You can buy these setups to do this, which are these big pots, and you put a whole bunch of oil in there, and they're usually on a propane base that heats up the oil to the right temperature. But you want to be very careful that these don't cause fires. These are well known to cause fires. In fact, there's some really funny videos by William Shatner from Star Trek fame where he actually shows these things. So you can Google that if you want and see him talk about this. Why does this happen? Well, when the turkey does have some water in the skin or associated with the tissue, virtually anything you drop in a deep fryer, you see those bubbles right away at the beginning. And that's because all the water is evaporating and making steam because of the high heat of the oil. And so that bubbles out. And once those bubbles are gone, then the high temperature of the oil can cook the food the rest of the way. The problem is when you have a turkey, it's so big that so many bubbles get released that it can bubble off the top. And if that happens, the oil comes down the side, and of course it catches on fire. So just be very careful if you use this method. So that's your public service announcement for today. Okay, so another way this has been used for a long time is called larding. This is where you add other animal fat, often pork, to lean meat. Usually you do that on the inside. I admire this picture I found online of whoever this is has really gone to town by putting bacon on the turkey. I'd love to try this. Although at a certain point you have to wonder, why didn't you just make a ham for this? But anyway, there are approaches like that. Or you can do what I do, and that is just avoid the turkey altogether and fix a duck. Ducks never have the problem of being too dry. This is actually, my family cooks duck every Thanksgiving because they're delicious. So I think it's a superior animal. Anyway. Okay, so I want to speed up a little bit because I'm running short on time, and I want to talk about a couple things about making other parts of the meal. So making gravy, this, just to be very quick about it, the general process after you've cooked your turkey, then you have these brown bits in the bottom. These are sort of your pieces of drippings, and they've undergone the Maillard reactions to make them very flavorful. You often dissolve these with a little bit of water. Sometimes you put a little acid in there, like a little wine or a little vinegar in there. You then come in and you do this step where you separate out the fat. You do this with one of these fat separators that you can buy at a cooking store, or if you're a chemist, you can actually use basically a separatory funnel. It's the same concept. In fact, one of my friends, Matt Sigman, actually uses a separatory funnel. I've seen him do it. But anyway, this will separate the flavor down here at the bottom, which you want to put into your gravy, and the fat is generally removed and thrown away or used for another purpose. You then always add a thickening agent. This is some type of starch, typically, most commonly cornstarch or flour, sometimes arrowroot. These are long carbohydrate chains, and the idea here is that they will go into the water of this as you cook it, and they will order the water molecules. All these OHs are going to interact with the water molecules in the gravy, and they're going to increase its viscosity. They're going to make it thicker, which gives it that sort of thick consistency that you want to put on your food, and that gives you your final product as you heat this to thicken it. One thing that's very important here is you usually pre-dissolve these in water first. If you don't do that, what happens is the particles will form a sort of crust around them like this. They'll form this gel of material on the outside. And when you do that, the inside can no longer dissolve. And so that leads to lumpy gravy, which is always a bad thing. And so usually you dissolve cornstarch in room temperature water first, or some other liquid. Flour, you actually usually pre-cook it with flour, which doesn't contain, or with a butter or oil, and that coats all the particles, and then you can actually dissolve them more readily. So generally that's how you make these thickened gravies. Okay, so one of the things about this, though, is that when you have a good gravy, especially for things like Thanksgiving or a meal that you prepped yourself, not with something in a can, you get this really sticky sensation to it. There's a really sticky feel to it if it's really well done, and it's very, very flavorful. And that's because it turns out there's protein in this as well. Okay, protein in this specifically set of juice and stock that comes off of the bird. And this might sound a little contradictory, because what I told you before is generally when you heat proteins, they become insoluble. They become these fibers that you can't dissolve anymore in water. And so why is it that some proteins actually get into these, carried all the way through the gravy and other types of foods? And that actually is because there is one special protein. So just to look back at this picture, so when we have these functional proteins, they unfold and then they start to aggregate. I'm really not drawing this picture very well because when I just use copy and paste, but it makes it look like these are all the same, like a repeating unit like this. They're not. They're all different ways. They're just not organized in any specific way. They're just all agglomerated together. They just all stick into each other in random ways. But one thing that is a very strong way that these do tend to come together are these hydrogen bonds between the strands. So these would be the chains of different proteins in these rows coming across here, separated by the red dots. And the backbone of these has both NHs and these carbon double bond O's. And these like to form bonds to each other. These actual bonds are what make these helices and sheets form that we often see in proteins. When they're just denatured and aggregating, the same types of bonds are happening. They're just not in any organized fashion. And so this is forming this long sheet where these red interactions are making the protein stick together. And that's why they don't dissolve anymore. Okay, sometimes some disulfides and things as well, but this is the main part. There's one protein in particular in meat especially, one protein that breaks this rule and does not have this problem. And that is the protein that you can actually extract and dissolve into water very readily. And that is collagen. And so collagen actually has a really interesting sequence. It's formed of three amino acids: glycine, proline, and then what ultimately is an artificial amino acid, hydroxyproline. The hydroxy group is installed later on when it's made. And this forms this sort of, this red, black, blue, red, black, blue, red, black, blue. This pattern repeats over and over and over along the collagen sequence with just a few other amino acids here and there. Well, what's interesting about collagen is I told you these NHs are interacting with these oxygens. And so that makes these bonds that hold these whole things together. This doesn't have the NHs, at least not as many. It's got this one here, but 2/3 of the amino acids don't have the NHs. And so you can see that they actually don't have that ability to stick together. So collagen forms both a unique structure. It forms this really interesting triple helix when it forms sort of connective tissue and the basis of skin and bones. And when you actually have it in, say, the turkey bones or the turkey skin or whatever, it dissolves because it actually doesn't form these same interactions. And so you can extract it. And so it is extracted usually using hot, but not typically heavily boiling water. This is how you make stock. This is also the process that led to the collagen that went into your gravy that has that thickening quality. And also one of the questions is, why does dark meat taste better than white meat in general? To each their own, but a lot of people do think that. And the reason for that is because dark meat has a lot more collagen in it. The collagen content is much higher, and it's usually found in a lot of the joints, such as the sort of leg and thigh joint that are found right adjacent to that tissue. And so it's because the collagen is dissolved and extracted into the water and moving throughout the tissue. So that gives it more of a mouthfeel, gives it more of that juiciness and that flavor. So collagen is very important for when this tastes better. The breast meat or the pectoral meat doesn't really have much collagen in it. And so you can make stock out of this, and this is now extracting that collagen so you can actually use that for making gravy and all kinds of other things in your cooking. Okay, so I'm going to speed up just a little bit, and I was going to talk about some of the different things you can make from this, but I only have a couple minutes left here. And so what I thought I would do is just talk about one more aspect of dessert making and talk about eggs just real quick, because this is something else you're probably going to run into in Thanksgiving cooking. And remember, I told you that if you have proteins, and we showed this with eggs, if you heat them up, they become insoluble. They become these, rubbery kinds of things and so forth if you overheat them. But it turns out you can control this process, and learning to control this process is really important for making desserts. And so what I mean is that if you have eggs and you sort of whisk your eggs together, you can actually add other liquids, which is most commonly milk or cream, and you can change the properties that it's going to have. You can change the temperature. You can give them more of a resistance to heating up so that you can heat them to a higher temperature before these proteins unfold and become insoluble. You can also dilute the proteins. Eggs are very concentrated in proteins. So when you solidify them, they are solid. Meat is also very concentrated. But if you can dilute the eggs by adding liquid to it, then when they do start to become insoluble, they actually keep the water trapped with them, and they form more of what we call a hydrogel, more like what you found with the collagen and the other gravies and things like that. So you can actually make a softer kind of gel if you add these liquids in there to dilute the proteins. And of course, with those liquids can come flavors such as sugar, vanilla, fruit, and chocolate. Okay, and so what we're talking about here is making custards. And so this is often found in many desserts, some of which are almost completely linked with Thanksgiving, such as pumpkin pie, where we actually use eggs and often dairy to hold this whole thing together, combined with some vegetable material, which is pumpkin, or you can put other things in there, and we're going to set this using heat. And so really the secret to making custards is that you want to do this slowly. You want to keep this unstirred. Okay, so in these cases, they're creme brulee, quiche, pumpkin pie, cheesecake. You don't stir these, and so they form this nice solidified mass that has just the right texture and consistency to it, because you got just the right ratio of proteins to the liquid. One of the things that is a real big problem is if you overheat any of these desserts, especially pumpkin pie. If you've ever seen pumpkin pie that's all cracky and maybe even wet on the top, that's because you heated it past the temperatures we've been talking about. And at a certain point, the proteins contract and the water is released anyway. And so that leads to that crack because they start to shrink and it leads to the liquid release, which you often see on the top of the pie. So don't do that. Keep your temperature right so that you actually don't overdo the top. One way to do that is often to cook the crust in advance, to blind bake the crust so that you don't have to bake the crust as long. You take it out whenever the top is done, okay? Now, the other way that you can do this is that you can stir these when you're cooking, and that's how you make a creme. And so creme anglaise, pastry cream, ice cream, these are all cremes where it's the same concept exactly. We're going to slowly heat eggs in liquids like milk. Ice cream is originally heated if you make it traditionally, and then you cool it down. And during this whole time, we're going to stir it. And when you stir it, that continues to have these proteins move around, and they don't set as firmly as they do in the other custards. And so you get a liquid hydrogel. So that's what gives the liquid consistency to all these. It's really just controlling two things. One is the amount of liquid in each of these, and the other is whether you stir it or you don't. So if you want something set, you don't stir it. If you want something that's not set, you do. Okay, so those are those two. Okay, I just have a couple minutes left. Maybe I will do one more thing. I do want to talk about one final thing, which is chocolate, and just clarify one mystery. If I can take just 5 minutes, if you need to go, I certainly understand that. And I will stick on late to answer questions, anything that you want to know. But chocolate is another dessert that's found throughout the year, maybe a little bit more common around the winter holidays, but it is at Thanksgiving as well. Chocolate is a fascinating material. You could give an entire lecture on chocolate because it's actually formed of these very complicated components. The major part is cocoa butter, which is fat. It's a largely saturated fat that forms it. But it's also cocoa solids. These are fiber, proteins, carbohydrates. These are pieces of the toasted cocoa beans that have been ground into a consistency. They're ground to a size of about 20 microns or so. It always contains a small amount of water, just the right amount of water. It has a lot of aroma components in there. Many different molecules are there, sometimes added, but hopefully not. And then finally, there's some natural detergents called lecithins that hold it all together. So these are sort of soaps, if you will, that make the water and the oil miscible with each other and sort of hold the structure together. So if you've ever cooked with chocolate, you probably run into a concept in dessert making, which is called tempering. And this is something that, again, unless you are a chocolatier or make chocolate desserts a lot, maybe you don't do very often, but sometimes you run into this out of nowhere when you're doing a holiday recipe. And I just want to talk a little bit about what that is and why you need to do it, because it's actually a really fascinating process. What tempering means is, you can sort of see here, this is an example I found on this website where these are 2 graham crackers dipped in chocolate. This has been untempered and this has been tempered. And what you can see is there's a very different look to this. It has a shine to it. It also is a crisper texture. It has a snap. So if you have a chocolate bar that you break, it's supposed to make a snapping noise. That's supposed to add to the excitement, if you will, of eating the chocolate, I guess. This also has a nice, firm bite to it and melts in your mouth. This type that's untempered does not. It's actually kind of a squishy, grainy chocolate. And once you eat it, then it just kind of melts slowly, but it's not quite the same experience as the one on the right. So anybody who's really serious about chocolate desserts will temper their chocolate. But what does this mean? Well, what it means is that chocolate surprisingly contains cocoa butter that crystallizes, that it forms these microcrystalline sort of areas in the chocolate. And I have pictures of that I actually found in some papers. So this is a scanning electron microscope, or SEM, of some cocoa butter that's been well tempered. And what we can see is it's got these sort of plate-like structures here, these plate-like microcrystals that are all stuck together like this in there. You can't see these crystals with the naked eye, but you can if you analyze these with electron microscopes. If you've ever seen chocolate that looks like this on the right, this is called bloom. And this is when chocolate sits out a little bit, and sometimes the heat will cause some of the cocoa butter to melt and seep out on the surface. So this white on the outside of this is just simply cocoa butter. It's completely harmless, except for the fact, if you look closely, there's a big old fingerprint on this chocolate. So I don't know if I'd eat this particular chocolate. Watch out for fingerprints. But this is sort of what the white stuff is. And this is actually an SEM of those crystals here. And you can see these are very different in what they look like than the crystals over here. This is what tempered chocolate looks like. This is one of the types of crystals you see for untempered chocolate. So it turns out that chocolate has 6 different forms of crystals. It's amazingly complicated for such what you might think is a simple thing. So cocoa butter has 6 different crystalline polymorphs, we say. And it turns out you only want number 5. You only want one of these, which is the shiny, smooth one that people associate with good chocolate. And so we have to get rid of all the others. And so here's the process you use to do that. These all have different temperatures that they melt at. And so what we're going to do is we start with our chocolate, and you heat this to melt all the crystals. We're going to heat this to about 115 degrees Fahrenheit. It doesn't scorch it, it just heats it enough. This goes all the way through these. It melts all 6 of these different crystals. And then we're going to very carefully cool that chocolate, not all the way, but only down to 80 degrees. And if we go down to 80 degrees, that's going to form all these top 3 in principle. Okay. This one, number 6, it turns out is very slow to form kinetically. So you don't actually get number 6 that forms in this process. You're only going to get a mixture of number 4 and number 5. Why don't you just, heat it into here? It's because number 5 doesn't form very well at higher temperatures. So this makes them both form at the same time. If we cooled it down further, we might start to form the 1, 2, and 3, which we don't want, right? So that's why you heat it to cool it to 80 degrees. You let it sit for a little bit, and then you heat it again back up to somewhere around 88 degrees. And the idea is we're going to go right in here, right in between these 2 temperatures. And that is going to be melting all the 4 that's left. And all you're left with is number 5. So that's the process. Heat it to melt it all. Cool it to let 4 and 5 form. Warm it up to melt any 4. So you're only left with the 5. And then cool it again. And those 5s will serve as little seeds in there. And they will grow the rest all as number 5. And so that's the general process of tempering chocolate. There is a trick you might run into if you bake a lot or cook a lot with chocolate. There's a trick, and those of you who've taken organic chemistry probably know this trick, and that is to seed it. Because it turns out another way to do this is to have your bulk chocolate, you heat it up, and you throw in some tempered chocolate already, and that serves as seed crystals that already makes it crystallize, and you actually can avoid the rest of this step right here. But if you've ever wondered why you have to do that, why you heat chocolate, cool it down, heat it up again, and cool it down again, it's this tempering to give you just the right crystal structure. Okay, so I just wanted to throw that in at the end. Thanks for humoring me with going over time. Where can you go to get more information about this? There's all kinds of sources. There's all over the internet. You can find things on chemistry of cooking. It's a very popular thing these days, and so there's many. Where I like to go, this guy here is sort of the guru. This is J. Kenji Lopez Alt. He's a hero of mine, and he basically has really dedicated himself to food science and understanding how these things work. He has a book called The Food Lab, which is a really good book that explains a lot of this. But really, this Serious Eats blog is where it's at. This is a great place to go. All kinds of different science in the kitchen kind of articles, and just articles about how to find the best hamburgers, or how do you cook this or that. It's a great resource. Here right now, I just looked today, and they have how to keep your gravy warm using a thermos, how to separate bacon fat and get rid of it, and how to try this on your own, how to keep your pie crust from getting soggy with Epsom salts. I have to read that before I'm going to try that. Anyway, a really good fun book to read about chemistry in the kitchen is this one, What Einstein Told Us to Cook. It's by a physical chemist named Robert Volka, which he writes in a sort of a droll fashion, and has user questions, people writing questions, and he answers those, and he has really funny answers usually. So I've really enjoyed this book. There's 2 or 3 volumes of it now. And then this is the sort of the Bible, if you will. This is On Food and Cooking by Harold McGee. This is an encyclopedic read of cooking. If you want, everything you want to know is basically in this book. It's also not really a page turner. It's more of a book that you would look things up in. It's fair to say. I have read it. It's an excellent book. So between all these, that's kind of where I go if you're interested in learning more. Okay. And so with that, I'm happy to answer more questions. And so just to catch up a little bit with what we have. Let's see. Vegan eggs, can you bake with these? I have to confess, I do not know. I would guess you can. I think that's where Googling is going to really be helpful. That's not a very good answer for me, but I would just check on that. I bet you can, because especially if they're largely protein, a lot of times you can use them in a very similar way. I bet they might have a slightly different ratio if you're making a custard or something like that. So, but I've actually not tried that. Yeah. And I'm happy. I'm going to catch up with the questions here. Anybody have more questions or anything you want to know? Just type them in the Q&A if you join late. I can stick around. Some people I know in the chat. Good to see you all. I can't see you, but good to see you virtually, I guess. Oh, and America's Test Kitchen. Yes. Thank you for pointing that out, Chuck. So America's Test Kitchen is also a great place to go. That is actually, Jay Kenji used to work there. Christopher Kimball's been associated with that and so forth. And yeah, so that's a really good one. One of the questions, why do I prefer a reverse sear? I'll tell you why. So I usually do this for prime rib, to tell the truth, not so much a turkey or chicken, but for prime rib, I always do it that way. I cook it for 4 or 5 hours at 225 degrees until the inside gets to be 126 with a thermometer, and then I take it out. And it's really convenient because you can cook that hours ahead of time and just let it sit on the counter because it'll stay warm for quite a while, and you can get all the rest of your food prep done and that kind of thing. And then when you blast it with that 500-degree heat, first of all, it makes that crust on the outside like I talked about, but it also keeps that crust crispy. I find if you do it early, inevitably you're going to let these things sit for a while. In fact, you should do that so the juices can redistribute. And so it tends to get soggy. That crispy crust is lost a little bit. So that's why I actually prefer it at the end. That's maybe my main reason. So thanks for asking that. Any other questions? Let's see. Any food-related insight on emulsification? Yeah, so emulsification, I kind of skipped my slide, but since you asked, I'll just go back to here. Emulsification generally involves most commonly this compound, lecithin. Lecithin is a component of the cell membranes of most types of cells. It is a phospholipid. This one technically is a phosphatidylcholine lipid. And this has a positive charge and a negative charge on it. So this is a water-soluble end. And then these long chains are the fat-soluble end. And so this is nature's detergent. This is actually how a lot of these solubility challenges or emulsification challenges are solved in cooking. So examples, if you make mayonnaise or hollandaise or something like that, those are both emulsions. So they are emulsions of a small amount of liquid, usually lemon juice, that is dissolved in a large amount of oil or a large amount of butter, if it's mayonnaise or hollandaise. So they're kind of the same idea. So that would be an emulsion where the bulk is the oil and the smaller component is actually the aqueous liquid. You can also flip that and actually have small amounts of a fat dissolved in a large amount of water-based liquid. It's just the same thing, but flip the other direction. So now all the blue tails would stick inside like this picture shows. There's going to be some fat globules on the inside, and then the outside is going to contact the water. It's just the same picture you've seen for how your laundry soap works, okay, except it's edible. Of course. There is one other source of these lecithins that's very commonly used. So the most common is egg yolks. So egg yolks have a lot of lecithin in them. And so that's what you use for these types of things here. But the other is mustard seeds. You might have seen this before. If you make a vinaigrette, one common way, that's oil and vinegar, and you want to emulsify that together, you can add mustard, add like a teaspoon of mustard to that, and that contains the lecithin, and it does the same thing. If you whisk it really well, you'll get an emulsion that's stable for quite a while. That'll stay together and put it on your salad or whatever you're serving with that, and then it will eventually split, but not that fast. So yeah, so that's how you do it with natural things. Of course, as you might guess, there's all kinds of synthetic things out there that people have invented, but for our purposes, we'll just focus on the natural ones. So. Let's see, trying to see if there's anything else here to with one oven, how do you get everything cooked at the right time? What a great question. And I don't have a great answer. That is really hard. That most of us fix maybe one or two things at a time for our normal, weeknight dinners and things like that. So once you have Thanksgiving, you got to cook all these things at once. The way that I usually just manage it. Okay, I'll just tell you, I set up a spreadsheet. The spreadsheet has all the half-hour increments on it, just like a timetable, and I plan it all out, how everything's going to go in and out because I am me. So it's got all those times. And really the trick is, especially if you're going to use these reverse sear type methods, get your turkey out of the oven as fast as possible. Also, bake your pies the day before. Or the morning before, get up really early and do that. Get those out of the way because the pies need to cool anyway. So get that finished. Then get your turkey in there, get that cooked, get it out of the oven. The turkey has to sit for 30 minutes at least so that the liquid redistributes. That's when you can throw in your stuffing, throw in your rolls and stuff, most of which cook around 350 at the same temperature. And then your gravy, You can usually use a stock and things like that to get it started. And then you can just add the pan drippings to that and you finish that up while your turkey's cooling a little bit. And if you need to, if you get a little behind, no big deal. That's what cocktails were made for. So give everybody a round of cocktails and put the turkey back in there just for a few more minutes at the end, maybe a high temperature to re-crisp it if you really want to do that. So that's how I do it. People have other tips on how you handle that, put it in the chat, because I really think that's really a challenge. Is managing all these dishes at once. So let's see here. Question about nutritional values. Do they change with low and high temperature cooking? I'm going to say not much. It kind of depends on what you're after for your nutritional values. Keep in mind that even if you cook food at a high temperature, the inside of the food is not at that temperature. Right. And so the inside is probably at the end of the day, like whether you sear a steak or whether you slowly cook a steak, or let's say you cook vegetables by pan frying the vegetables, or if you actually steam them or boil them in water, all three different temperatures. I think that they've done studies on this and there's no real difference in the nutritional content in the bulk. The outside might be different. Generally, the higher heat, the more Maillard reactions. And so you've done some destroying of those molecules, but that's only the thinnest part on the outside. So I would say, in most cases, there's probably very little change in the nutritional content. I say that with caution because it's hard to make generalities, but that would be my answer. So, any tips on baking pumpkin pie before overheating that cracking situation? Yeah, so great question. So I have made pumpkin pies a few times. First is a good recipe. Drain your pumpkin. So a lot of times the canned pumpkin, which you use, it's pretty wet. So I put it in a strainer and let the liquid naturally, by gravity drain out of that a little bit and get rid of some of that. Because if you have too much liquid, that can cause that problem as well. Another one, by the way, there's always this debate about should you roast a pumpkin like the one behind my head and use that from scratch. And I think the general consensus out there is don't bother. For two reasons. One is that cooking pumpkins is a real pain if you've ever done it, especially a big one like this. And so that's just decorative in my house anyway. The second thing is, as it turns out, what you think of as pumpkin pie and what you buy in the Libby's can for pumpkins isn't pumpkin. It's actually more of a butternut squash. There's a specific squash that they grow in Indiana, I think it is, and that's actually what they can and put in there. So it's not exactly pumpkin anyway. So if you cook one of these field pumpkins, it usually doesn't taste right. And they do tend to be stringy, grainy, and have a lot of water content. So don't do that. So use this stuff in there. And then I think just to finalize that answer, I would just keep your heat modest. Don't overcook it. And again, usually where people run into trouble is the pie is done on top, but they look at the bottom and the crust isn't done yet. So pre-bake your crust might help you. You can do that with putting some, weights in there, like crust weights and make pie weights and things like that. Or you can use beans and something and just cook it. And then you use that shell. On the Great British Baking Show, that's something you see them do all the time. So they don't get the soggy bottom. So let's see, trying to keep up with some of these. Pressure cooker. Yeah. Pressure cooker is great. And you could definitely, so the pressure cooker cooks things fast. It also often is with a high amount of liquid because it's, steam pressure. And so that can work. I haven't done that for a turkey breast. I've done that for chicken breast and it's way more moist. It's actually delicious. And then if you had skin on there, then I suppose what you would do is the high heat blast at the end. I haven't tried that, but you could do it. You can also just pan fry it with the skin down. That's another way that you could do that. So that's I think a great idea. The trick with the turkey, of course, is having a pressure cooker. Like it'd be terrifying to have a pressure cooker large enough for a turkey, I would say, because that's like that's like a bomb. But maybe there's a good way to do it. Yes, you can cook the turkey in the barbecue. I'm actually going to do that for the first time this year. Thanks for bringing that up. I'm actually going to try this to smoke it on the barbecue out back. Thought I would experiment this year. Thanks for bringing that up. Okay. And my spreadsheet, I'd be too embarrassed. I'd be too embarrassed. Let's see. And then, so yeah, I think there's all kinds of vegetarian options for this. What I would do is think about the sides and the stuffing. So, some people really, I guess, they really like Thanksgiving because they really like the turkey part. I've always been the kind who likes the sides anyway. So I love mashed potatoes, green beans or chard, or if you have, stuffing and those kinds of things. All of those can be made vegetarian very easily. And so I would just focus on that. you don't have that sort of main centerpiece. But again, a lot of people who are vegetarian don't mind that anyway, right? So I myself would have no problem just sitting down with a completely vegetarian. In fact, I've done that. Had a vegetarian Thanksgiving, and it's actually delicious. So yeah. What I haven't tried so much, I don't know if any of you have, is some of the alternative, there's tofurkey and all this. I haven't tried some of those other things in there. So I don't know what the mileage is on that. But what metal do you recommend for a pressure cooker? Well, okay, aluminum, yeah, aluminum. So there was for a while this idea that aluminum can lead to dementia. There was some reasons people thought that biochemically. My understanding, I'm not a doctor or physician at all, but my understanding is that has been debunked. That connection has not been validated. And so in fact, I don't think people know any scientifically validated connection between aluminum in your diet and dementia per se. That said, there is a reason not to use aluminum in a pressure cooker or a pot, a big pot. And I mean, by aluminum, I mean bare aluminum. And the reason for that is a lot of foods contain acid, and that acid will react with that aluminum. So anything with fruit in it, or a little wine, or a little vinegar, if it's in there, will react with that, and it actually will make this sort of gray, sloggy stuff in there. So I don't recommend that. It's if nothing else, doesn't taste very good. It's kind of metallic-y, and it doesn't look good. So generally, most people you can have aluminum in your cookware, but most people line it with stainless steel. So most pressure cookers I know, so I have an Instant Pot, but most of those are stainless steel lined. Or if you cooked with Calpon or something like that, those are usually anodized. So the surface of the aluminum is an oxide that's a very hard oxide coating, and it protects it from that to some degree. So yeah, but for pressure cooker, usually it's stainless steel or stainless steel coated something or other. And then the other thing, if you're not doing a pressure cooker, of course, glass is also or ceramic is a good way to cook sometimes. Yeah, depending on how you're heating it and so forth. What is the chemistry behind seasoning a cast iron pan? That is cast iron pans and grills outside, and also woks, all these kind of things. What you're doing in those cases is that there's a coating of basically pyrolyzed fats on there, that all the organic molecules in there have spit out a lot of hydrogen. They've spit out a lot of water molecules, and what's left is basically this carbonaceous material that just coats it really well and tends to resist sticking because it coats all the little pits. What makes things stick is metal have all these little pits in there, and when food gets on top of that at a high temperature and then it cools down, there's like a vacuum and it sucks it down in the pits, right? And so that coats all that on the bottom is how I think that works. And so usually for seasoning, you just have that coating that's been polymerized on there. And as long as you don't scrub it real hard, you leave it on there, then food doesn't really stick so much. That's what I know about that. So yeah. Any other questions? Sorry if I didn't get to any of the questions that you asked in there and I missed it. Okay. Well, if not, everybody have a nice Thanksgiving. Maybe I'll go out of the share thing here. So have a great Thanksgiving, everyone, and we will see you later. Bye.